All right, so here we're taking a look at a voltaic cell, and when we're taking a look at voltaic cells, we still want to figure out what's reacting. So what we have is just some cell notation. We have the first half cell, the second half cell, and it's not together, they're in different solutions, and that's why we have this phase boundary with those double lines. So we'll go through your data booklet, still identify your OAs and your RAs so we know what's reacting. So you have zinc solid is an Ra, zinc 2 positive is a OA, copper 2 positive is a OA, and copper solid is a Ra. Then your strongest OA is copper 2 positive, and that reminder, OAs undergo reduction, and reduction now, which we'll know happens at the cathode. And if you didn't know, now we'll just add that information. So the metal called the cathode is the site of reduction. Your strongest reducing agent is zinc, and reducing agents undergo oxidation, and that will happen at the anode. So when you go to draw the diagram, you will always have two beakers. You will have your electrodes, which are your metals. You will have a conducting solution in each of those beakers, and you'll have a metal wire that's connected to a voltmeter, and that's where electrons travel through. And then to complete this circuit, we must have a salt bridge. So it does tell us that our salt bridge contains sodium sulfate, so we'd have Na positive ions in the salt bridge and SO4 negative 2 ions also in the salt bridge. So going through this, usually we draw our anodes on the left and our cathodes on the right, but they definitely could be switched. We do know our anode is zinc metal. So zinc here, sorry, that's a little bit messy. So try that one more time. There we go. So we have our zinc, that's not, there we go. There, hopefully that works. Our zinc solid, and then you'd have zinc 2 ions floating in solution. Now this ion can't exist by itself, so it's most likely paired with another spectator ion, so I'm just going to put NO3 in here, and that would all be floating around in solution. On the other side, your cathode, the copper metal will be your cathode, and same idea as the other half cell, you'll have copper ions floating in solution. That wouldn't occur just by itself, so we'll have another spectator ion. So this is the original setup of what's happening. We've now labeled your electrodes. That would be your anode and your cathode, so we have that down. Electron always flow from your anode towards your cathode. So we have now that labeled. Your voltmeter is the wire that connects your anode and your cathode, so it's connected to that. The direction of ion flow. So here, when we're taking a look at what's happening, your zinc metal will break apart. So once this reaction starts happening, because it is spontaneous, zinc solid will break down into zinc 2 positive and 2 electrons. Now those electrons need to go somewhere, so they are going to leave this half cell and go into the wire. This zinc 2 positive needs somewhere to go as well, because now it's not solid, and it will end up going in solution. So this zinc solid is getting broken down, and if it's getting broken down, that means it's going to decrease in mass. On the other side, you have electrons coming over to the cathode, and so now we have electrons hanging out on this cathode. Negative will attract positive. So these positive copper ions are coming out of solution, so they're going to join with those electrons, and every ion will need 2 electrons, and it's going to make more solid. So coming out of solution, joining with those electrons, and then adding mass to the original copper that was there. So far we have the direction. We also have added on what's increasing and decreasing in mass. Now let's look at the direction of our ions, how they're flowing. So when we take a look at, let's say, the anode first, as your zinc is breaking down and you're getting more and more zinc 2 positive in solution, what ends up happening is there's a buildup of positive charges. We need to neutralize those positive charges. So the negative ion that's in the salt bridge is going to come travel down and neutralize those charges. On the right-hand side where the cathode is, as the positive 2 copper comes out of solution, it's leaving behind an overall negative charge, right? Because the NO3 negative isn't coming out of solution, just the copper 2 positive. So that buildup of negative is going to attract the positive ions from the salt bridge. So the positive ions move towards the cathode. So that's how we have our movement, and I think we have basically everything here. The other part just to add on here is anodes are known to be the negative terminal and cathodes are known to be the positive terminal if you're looking at a voltaic cell. And then you can also add on with the half reactions, which we haven't done yet, but that's just what you're used to. So if you know that your copper 2 positive is undergoing reduction, then you can write down that half reaction just how you see it in your data booklet. And if we know that the zinc is your reducing agent and is being oxidized, we can flip the reaction that you would see in your data booklet to show zinc breaking up into its ion and into electrons. Then we don't need to multiply anything because your electrons are already balanced. So you can add these 2 half reactions together to get your net ionic equation or your redox reaction. So we have that plus zinc 2 positive, and you're always above your Ra, so this reaction would happen spontaneously. And within this voltaic cell, you're turning your chemical energy into electrical energy because you are getting some voltage. If you found this video helpful, please subscribe. And if you would like to see any other type of video, you can leave me a comment. Thank you.